because the data set has just two pictures. So you can plot it on the 2D surface like this. So one axis is for one picture and this for the other picture. So let's now say you have three pictures. Plot that. You can plot three pictures on the 2D, like having two axes for three pictures. So you need to introduce another axis for the third picture, right? So let's say this is now x3. It becomes x2 and x3. So you just get a 3D plot of your data set. But what happens when your data set has four pictures of your data set? But what happens when your data set has four pictures? It becomes difficult to visualize when you have. Okay, so it becomes difficult to visualize when you have more than three pictures. So what you use PCA for in terms of doing dimensionality reduction is you having several features. So you can use PCA to reduce the dimensionality of your picture matrix to have say two features, then you can visualize that. So we mostly use it in something called EDA. So EDA stands for exploratory data analysis. So let's say you are given a problem to solve, you have a data set. The first thing to do is to explore your data. And in exploring your data, you want to be able to visualize the data. And to visualize the data, probably the data has 100 features or 10 features. So using PCA, you can reduce the dimensionality to like maybe 3 or 2 that you can visualize on your 2D surface, like the board, or just use Matplotlib and plot the 2D plots of your data set. Then there's also one other thing. You can also have a redundant feature. So let's say you have a data set. You can also have a redundant feature in the sense that you having a data set of like, let's say 3 features, where one feature is dependent on the other. So meaning that the third feature is actually redundant. For example, so let's say you have a data set with 3 features, first, second, third. Then this third feature is actually dependent on this. In fact, maybe the third feature is actually probably a multiple of the second one. So let's say your data points are 1, maybe 3, 6, 8. Then here you have 2, 6, 1, 3. Then here you have 4, 12, 2, 6. So who can tell me something about this second feature and this third feature? Yeah. So from what you can observe here now, like x3 is actually 2x2, meaning that by just doing x2, we've known x3. So why do we still have x3 there? So x3 is a redundant feature. We actually don't need it. So we can do away with x3. So we can do away with x3 and just work with 2 features only. And this is dimensionality reduction. So we reduce from 3 features to 2 features. Okay, so how do we now apply PCA? We all know the reason why we apply PCA. So we apply PCA to reduce the dimensionality of our feature matrix. So maybe having 100 features, we want to reduce the dimensions. So Well, that's why we apply PCA. Then the outcome of doing that is okay. The reason why you do that is because you want to visualize your data set. So you want to be able to project maybe a 100-dimensional picture into maybe a 2D into 2D dimensions, so that you can be able to visualize it. Then also another reason is because probably you want to see the dependence of one feature on another feature in order to know the feature that you can knock out. So you having like 100 features, some features can actually depend on others. So you can have redundant features, and using PCA, you can remove those redundant features and you will be left with the features that you can use for your learning algorithm. Okay, so that's just the explanation of PCA, what PCA is, why you use it, and what you use it for. So how do you now use PCA? How do you use PCA? So these are the steps for applying PCA. So the first thing you do is to obtain something called a covariance matrix of the feature matrix. And after obtaining the covariance matrix, you perform something called eigen decomposition on that covariance matrix. And after doing the eigen decomposition, you then obtain the eigenvectors. And these eigenvectors are the principal components. So once you get the eigenvectors, you are done. So you've gotten the principal component, then you can now project your original feature matrix using the principal component. So you get another feature matrix representation of the original one using your principal components, which are the eigenvectors, and that's all.
Can you explain
Eigenvectors. No, I'll get there. Later. Okay. So actually, like there are a lot of maths here, actually, because you'll be finding mean, finding variance, finding covariance. You'll be doing something called your eigenvalue decomposition. A lot. You'll be working with maybe orthogonal matrices, orthonormal matrices, and all that. So I'll try as much as possible not to go into that in detail. So I'll just treat them at a very high level. So and actually in scikit-learn, to use PCA, just like you can just call you can just instantiate a PCA object from scikit-learn and initialize all the parameters, then use that to perform PCA. But what we are going to do in this code lab is, actually to understand how to apply PCA from scratch. Using the covariance matrix, using the eigenvalue to get the transformed feature matrix. So that's what we're going to do. And when we are done doing that, we then use scikit-learn with like 3 lines of code. You can do that with scikit-learn. Let me just show you the scikit-learn implementation here. Okay. So this is just state. So with scikit-learn, so from sklearn import decomposition, then so this is the PCA class in decomposition. So you just instantiate an object from this class. Number of components you want, 3. Then PCA.fitTransform, get this, and that's all. So this is now the new representation of the feature matrix. But before we get there, let's start with NumPy. So we are starting with NumPy. And how things work. So you just get a toy example and work with that. A very simple feature matrix that has just 4 examples and how many features? So it has 3 features here, 3 features and 4 examples. So I'm going to apply this, I'm going to use this feature matrix to explain. So this is just saying that x is equal to something like this. Right? So like this is like a set of real numbers of this dimension, which is something like this. So you can view this as a set of real numbers having this dimension m by n. So I'm saying that x is example in our training set. So what we want to do in PCA is to find another representation of x. So let's say to find x prime. Okay, let me not use x prime. Let me use x2. Yeah, to find another x, and you find this x by applying a transformation on this. So you are meant to transform this matrix into this one. So you just apply this transformation, probably p, then x. So this is what you do in PCA. So you have your principal component, which is represented by the matrix like this.
Just go back to that.
Can you all see it?
Lawrence, use another one.
You have a black one.
Yeah.
Red, red, red.
Still space.
Can you all see it? Okay. So this is basically what you do here. So you have a principal component matrix. Then you use this principal component matrix, which is the matrix of eigenvectors. Use it to transform your feature matrix to get a transformed feature matrix. So let's say you want to transform this. So these 3 features, right? So let's say you want 2 features, like you want to knock out the 3rd feature. So mean that this matrix here is going to be of size. Okay, so you having 3 features means that your matrix of eigenvectors will be of size 3 by 3. Because you are going to find a covariance matrix, and that covariance matrix will be of size 3 by 3. Then when you do the decomposition, you get a matrix of eigenvectors of size 3 by 3, which is this P. Then you apply a transformation with this P on your feature matrix. So you just have a dot product of this and your feature matrix. So in this case, you know what the size of your feature matrix is. So the size is typically the number of examples by the number of features. But in this case, we are going to use the other, like we use, okay, dot. So we are going to use 3 by n. And you know what I've just done to this feature matrix? Yeah. Then you get 3 by what? M as your x2, which is like this, which is similar to this also. Yeah. I wanted to reduce it, but getting okay. So in this case, I didn't reduce the number of features. Like I just got the transformed matrix using the matrix of eigenvalues. But in the case whereby I want to reduce it to like 2, so this P here will 2 by 3. So when I do this transformation, I'm going to get 2 by m. So meaning I've reduced this from having 3 features to 2 features. And how did I get this 2 by 3 matrix? So I got this, I got it by also performing eigenvalue decomposition. So initially, what I had was 3 by 3. Right? I had 3 by 3 initially, telling me that this is a matrix of eigenvalues, and a matrix of eigenvectors, and I have how many eigenvectors? 3 eigenvectors of dimension 3. So this is something like this. So one eigenvector here, another eigenvector, another eigenvector, and each eigenvector is a 3D vector. So for me to get this, I'll have to probably take the top 2 eigenvectors. So probably taking these 2 eigenvectors. Yeah. And what determines this choice? Like, why do you take these 2 and leave out this one? So like this actually comes from the eigenvalues. So in essence, each eigenvector has a corresponding eigenvalue. Okay. Okay, but we all understand this part of using this matrix here to transform your feature matrix.
Is that clear?
It's clear now, right?
It looks like we have another class at the back. Right? Guys, are you with us? Are you with us?
What is
What's your name?
Okay, what is I will explain eigenvectors and eigenvalues. Like, just know that eigenvector is a vector, like a special vector.
What's the name?
From
the feature matrix you have, you get the eigenvector.
No, I'll get there. You actually get the eigenvector from the covariance matrix, but I'll get there. So just know that the eigenvector is a vector, like a special vector. Then it has an eigenvalue, which is this. So, but we all understand this. Just apply a transformation to the feature matrix. This one here, like, it's clear. It's clear, right? Okay. So let me now. Let me now go back. So we all know what mean is. We know mean, yeah. We know mean, and we know. We don't know mean. Okay. So you know what? You know this, right?
Yes.
And you know this.
Yes.
And you know this. Yeah, you all know everything. So this is the mean, this is the standard deviation, and this is the variance. Okay, very, very good. So there's something called there's something called variance, and there's covariance. So what do I mean when I say variance? So when I say variance, I'm just trying to say, like, I'm trying to tell how much my
Something deviates from
value is. And this one has F, E, A, I, A. Right? So you can find the mean of x1, right? So the mean of x1 is just you add everything and you divide by the total number of outcomes or values. Then you can also find the mean of x2. Then you can find the variance of x1. So what's the variance of x1? The variance of x1 is just saying how much each of the value, like, differ from the mean. So it's just something like a minus, let's say the mean for x1 is mu1. Let's say the mean is mu1. So the variance is just saying, it's just telling you, like, how much it deviates from the mean, each value. So you just find the average of this. So the average of this. So you get a minus mu1 squared, right? So you find the average. So you do this for each example here. So you do this for A, for B, C, D, E. Then you find the average. That's the variance. So it is just telling you like how much each value deviates like from the mean. And there's also covariance. So covariance is actually comparing two random variables. Like you all know what a random variable is, right? Yeah. So like x1 is a random variable, x2 is also a random variable, right? So for covariance now, so you find the mean of this, which is mu1. The mean here is mu2. So you know that for variance, what we did was just to subtract the mean from each element, and then we took the square and found the average. So for covariance also, we'll do the same thing, but in this case, we'll consider two variables. So the covariance is now going to be x1 minus mu1 times x2 minus mu2. Then you find the average. So probably for the first example, it's going to be A minus F. For the second one, it's going to be B minus mu1 times G minus mu2. For the third example, it's going to be C minus. Like you calculate everything, add it, divide by the total number of elements, and that's your covariance. What is this? Where is the light?
And they're fixing it.
You fix it fast, bro. Before okay. Okay. So I mentioned something about the covariance matrix. So the covariance matrix is simply this. So let's assume you have three features. 1, 2, 3. 1, 2, 3. So this for the first feature of the first one of the first feature. This is the variance of the second feature. This is the variance of the third feature. Because this is 1, 2, 3. This is 1, 2, 3. So here is actually comparing, like I'm comparing the first feature with itself. So it's going to be a variance. But here now I have the first feature, I have the second feature. So this is going to be what? Covariance of the first feature and the second feature. This is going to be a covariance, like let's say 1, 2. So here you have covariance 1, 3. You have covariance 1, 2. You have covariance this 1, 2. This is what? Covariance what? 2, 3. This covariance 3. This sorry. I've missed it. This is 2, 1. This is 3, 1. 3, 1. This is covariance what? 3, 2. This is the covariance matrix. So this matrix captures the variance and the covariance. So it is simply telling me that okay, covariance. So it is simply telling me that okay, my feature matrix has 3 features, and this is the covariance matrix. So this matrix captures the variance of x1, variance of x2, variance of x3. It also captures the covariance between x1 and x2, covariance between x1 and x3. Like everything is here. And there's one thing, like when you find the variance, like okay, when you find the covariance between two features that are maybe highly related. So let's say in that example now, like I gave an example earlier where I had like I had like three features. Yeah, where x3 was equal to 2x2, right? So I had like three features then, and the last feature was kind of redundant because it was actually a multiple of the second feature. So these two features are highly correlated. So if you calculate their covariance, the covariance is going to be greater than 0. So it's going to be probably up to 1 higher. So meaning that they are highly correlated. Then let's assume this is minus 2. Okay, just from here, if this is minus 2, meaning that the covariance between these two is going to be less than 0. So probably you have something like this. Can I write here? Yes, okay. So just know that if you have a covariance that is high, that is greater than 0, then it means that those two features are highly correlated. Then if it is less than 0, it also means that they are highly correlated, but the correlation is what? Negative. So partly you have okay, can write here. So let's say you have this guy here, this guy, x3 against x2. It will obviously give me something like this. So the scatter plot of these two will give me something like this. And sorry. So this meaning that x3 and x2 are highly correlated. So the covariance is going to be positive, it's going to be high. And if you have something like this, this is going to be in, like, you will get a negative covariance for this, because like as this one is increasing, this one is reducing. As this one is increasing, this one is reducing. So you are going to have a negative covariance for this. Then if you have this, so like what can you say about the correlation of these two? It's scattered. So they are not related at all, right? So the correlation is going to be 0, and the covariance is going to be 0, right? So your aim is for you to have what? Covariance to be 0. Like you don't want, like you saw that example I gave earlier. I had x1, I had x2, I had x3, and x2 was dependent on x3. X2 was dependent. So I had to know. So your aim is that your features should not be dependent on on other features. So you should have something like this when you plot a scatter plot of your features, maybe x3 against x2. You should have this, and this is the goal of PCA. Yeah, not really PCA. Yeah. Okay. Yeah, this is the goal in terms of removing redundant features. Like the goal of PCA is for dimensionality reduction, and a sub goal is to remove redundant feature, because one goal is also for visualization, like you want to be able to visualize your data. So meaning that when we have a covariance matrix like this, what can you say? What should you say about this value here? So this value is actually the covariance of feature 1 and feature 2. So meaning that this guy should be 0, right? Yeah. Because like you don't want features to be related with other features. Like you don't want the correlation between one feature and another feature to be high. Like you want them to be independent. Like you don't want dependence. So meaning that this guy here should be 0, right? Yeah. Or if not 0, it should be close to 0. This guy should be 0, 0, 0, 0. Then what can you say about this one, and this one? It should be 1, right? Or high. Because you are just plotting. What you are doing here is just you have x1 and you have x1. So x1 against x1. You just get something like this. You get. So x1 should be highly correlated with x1 because it's the same thing. x2 should be highly correlated with x2. So when you have a covariance matrix like this, the aim is to so let me come here now. So you have this. Hope you can still remember this equation here, right? X has a covariance matrix, right? Which is this. And x2 will also have a covariance matrix. So what we do here is to find x2 that will have a covariance matrix. So when we apply this transformation here, the x2 that we have should have a covariance matrix that is something like this. Right? This is the goal. So meaning that the transformed picture matrix that we should get by applying PCA should have a covariance matrix where each feature only depends on itself and doesn't depend on other features. You all understand?
So,
Yeah.
So in essence, what we're trying to get x2 so that is only along that's only related to everything else.
Yes. Yeah.
So P doesn't be any way that will give us that value.
Yes. But x2 is not this, so like this is actually x2. So this is the covariance matrix of x2. So we want to get an x2 that will have this type of covariance matrix. So this may not be 0, but it should be close to 0. This one should be close to 0 also. And
P will help us find
yes. So when you do this transformation, like you get this, and what should P be? Yeah. Why? Okay. I said earlier that P is a matrix of eigenvectors.
Yeah.
Wow. You guys are smart. Okay.
Well, what would like?
Or if they don't like, it's not like totally mess with you get so like you are learning something and someone else is sneaking his nose into your learning like just take that bad guy out because it's not adding anything. It's not adding anything.
And an example, you give an example, practical example of independent variable. Maybe like you have length of, you have imaginary area and
area.
When you have meters, when you have inches and meters, so
Yeah, inches and meters because there is just a multiple of the other one. Yeah.
When we plot and this map plot.
It's now.
Yeah.
Okay.
When the correlation.
Yeah, that's
When
cool.
we have 0.5
Yeah.
as the correlation, you need to check
It's
that.
okay.
You need to
As
check
what? Correlation?
Yes.
0.25. Okay, we don't
0.5.
0.5.
Yes, if that
Wow.
particular variable
0.5 is kind of it's high. It's high. It's not actually. It's in between anyway. Like it is correlated, but yeah, not strongly correlated. That's positively correlated. Okay. So
Any question?
yeah.
What we have minus something.
minus something. That's the negative correlation.
So if you have minus 0.52, it's a problem because it's still correlated, but it's correlated with a negative.
So what would be our gain when we are plotting that?
Zero.
When you have
That and it's not plot, showing us the prediction, like
it's showing me the correlation now.
like what should we look out for, like
I'm not sure. What
Your aim is
based
to
on? Is it
like
based
your
on-
aim is to get something
is it
like
based on this
so
or
that
just
heat map
correlation heat map? I think
that heat map should give you something like this. You should have this. This guy should be thick. Then every other thing should be light. It has the like it has what it should give you. Like if it's giving you anything else, it probably here is kind of dark. Or maybe 0.9.
So we can say that
Things that this one and this one they are highly correlated. So you can just drop one. Huh? No? Yeah, somehow. Okay. Okay, so there's something called covariance and there's another thing called correlation. So like heat map actually shows you the correlation. Like it will show you the correlation. So correlation is usually is just like a normalized version of covariance, in that the values are from -1 to 1. So like correlation is actually covariance over what? Over
What the number?
over sigma 1, sigma 2, right? Yeah. So let's say this is the covariance between picture 1 and picture 2. So the correlation is just the covariance, like it's just a normalized covariance. Like, right? So meaning that what you get for your correlation must range between -1 and 1. Then covariance is not normalized. Okay, so yeah. What else? Okay, so we were here, right? So the aim is to find the P that will satisfy this condition. Yeah. Okay. So let me clean this. Like, are we enjoying the maths? Right? Like, we're enjoying the maths, right? Let me just continue with maths. Okay, so you have this. You have okay. You have Cx to be what? So there's actually a formula to find covariance using a vectorized approach instead of doing a division of everything and then dividing. So you can just use a vectorized approach. So you have one vector or matrix, multiply another matrix, then you divide by the total number of rows. So it's something like this 1 over m. Then if this is your x, maybe xt x. So this is the correlation. Sorry, this is the covariance. But mind you, it's going to be something like this. Right? Because this is how you find covariance, like deviation from the mean. Then if you do this, like those of us that are familiar with linear algebra and matrix multiplication, you discover that when you do this is just having this one times this. Like this is just like some summation of everything, like of this and this, like a sum of products. So you have products and you're adding them. Right? You have this. You have A, B, C, and you have A, B, C. This is a squared plus b squared plus c squared.
Oh,
That's what this is. Like, anyway. So that's basically what is happening here. So, and this will give you the covariance. This here will give you the covariance. But we all know of feature scaling and okay, let me write it down. Like we know feature scaling now and normalization. So what do you do in feature scaling and normalization? You just subtract the mean and divide by the standard deviation. Like when you perform feature scaling and normalization, what you get, the normalized feature matrix you get will have zero mean, right? And the standard deviation is going to be 1. So this is what you get when you perform feature scaling and normalization, which is does this. So doing this for feature scaling and normalization, we do this. Then our new feature matrix is going to have a mean of 0 and standard deviation of 1. Fine. Meaning that if we are to apply this on a normalized, this guy is going to be 0, right? So we are going to have something like this. So and the same thing should apply for x2 also. So this should be right. So this is the covariance matrix of x2. And we all know what x2 is. Clear? So I can clean all this. Sorry, like I'm solving maths. I'm meant to be. Sorry. Wow, nice. Okay, so this x2 is the transformed feature matrix. Then you have this 1 over m is dx transpose, right? And you have dx again. This is just putting this guy here. So this is now what? This, like, we all know this, like, if you have something like d transpose, that is going to become what? This will become b transpose, a transpose.
yeah.
Right? So this is now, what is it again? This is x transpose, right? Okay, this is x transpose, this is p transpose, this is p, and this is what? X. So there is actually a twist here. There's a twist here in that if we have x, okay, let me come to the twist. So x2 is actually of what shape? X2 is actually of what shape? M by okay, let me not start with that. X is of what shape? M by n, right?
Yeah.
P is of what shape?
M by M.
N by right? This is n by n because we have n feature codons. Then finding the covariance matrix, we get n by n, right? Because we're going to do this. So this is not going to work. Actually, it won't work. Definitely, will it? Yeah. It won't work. So meaning that x2 should be n by m, right? And if this should work, then x should be what? Fine. So meaning that my x2 is actually px transpose. So You said? Where is it?
So it won't be heat transport, transport. So that was the notation you use.
I want what?
Just
Notation you use.
just reflect.
We here.
Yeah.
I don't understand.
We still get heat transport, transport.
Where? Here.
Yeah, that. Yeah.
P transpose X. What are you saying?
What I'm saying is P X transport.
Where is it? Here.
Yeah.
Okay, P. Okay. Yeah, P. Sorry. This N times N, right?
Yeah.
This is what?
N by M.
So this should be N by N. We give it this. Yeah. Right? So this should be this. So meaning when you come here, you get this. And you have this. Something is wrong. Okay. This is what this is what shape is with this guy? This is what you battle with, like battle with. This is N by N. And this guy is definitely N by N. So this is actually wrong. So this should be N by N. Right? So this is going to give me N by N. So something is wrong. So this should have been something like N by N times what? Times N by N times N by N. I see what I'm doing here. I see what I'm doing here. So this should be something like P times this N by N, right? So this is like X transpose, right?
N by N is X.
This is X. Then times N by N again. Something P to give N by N. So I've actually mixed up something somewhere.
No, actually, I think what I was from there, you could still have.
I don't know.
From there.
So this is CX2, right? So it's not going to be. So something is wrong here. So I'm meant to get this. So this is 1 over n. So this is now going to be P. This is scalar, right? So you can just come here. So this is xt, this is x, this is p. This becomes p. Sorry, this is p transpose. So this is p transpose. What was this here? This guy is this guy. Right? This here is this. So it's now going to be this is C what now? CX P CX2. So like let me just leave that. Okay, so you can all see this here. So we have this like I did here. So Cx is this. So this is actually Cx2, but I just made it Cx prime. So this is the covariance matrix of the transformed feature matrix, which is this, and this is so this is the transformed feature matrix. So let me go up to my equation here. Yeah. So this is the mix up here. So I'm actually meant to have this. So this, yeah. I can clean this. So the aim is to find x2, right? the aim is to find x2, which is equal to. So this is just like x2 is transforming x with p, right? So like what's the shape? So p is actually n by n. X is what? Let's say x is n by n, and x2 is what?
N by.
It's n by n. Or you can, but we all know that x is not n by n, right? X is actually n by n, right? Then p is n by n. So what I did was to put this here, transpose something. So this became n by n to give n by n. Or you can do this equals something. Then just play with the shapes. Just play with the shapes. That's not fun. Okay, so at the end, you are meant to get something like this. So you have your transformed, so you have the covariance matrix of your transformed feature matrix as this. And you know what this should be, right? This should be a diagonal matrix with the other side 0. Like that's what you want to achieve. You want to achieve that. And then you know what Cx is. You know Cx. Cx is actually a symmetric matrix. It is the covariance matrix, and covariance matrices are always symmetric. Why is that? Because this is equal to this, right? You saw the covariance matrix where it was. Yeah. So the covariance matrix is symmetric. Something like this. So we have bar, and this is like the symmetric matrix. So meaning that the value you get here will be the same value you get here because of here. So there's something called an orthonormal matrix. You know what an orthonormal matrix is? So orthonormal matrix, or let's say orthogonal. I can't even spell orthogonal again. Orthonormal. Okay. Now, so like just taking that for an orthogonal matrix, the transpose is equal to the inverse. And the same thing applies to the orthonormal case also. So there's this theorem, like for those that do linear algebra. So if you have a symmetric matrix A, let me write it here. So if you have a symmetric matrix A, and you apply to let's say you apply an orthogonal matrix like this to the symmetric matrix, you're going to get the diagonal matrix. Like this is a formula in linear algebra, like proven, so I don't need to prove it. So this is an orthogonal matrix. This is an orthogonal matrix. This is symmetric matrix. So when you do this transformation, you're going to get a diagonal matrix. Okay. So like it's all here. So you're going to get a diagonal matrix. And this diagonal matrix is going to be is going to be one that have like is going to have the eigen values of this symmetric matrix. So that was what we are going to apply here. So meaning that for this guy to be a diagonal matrix, right? Then these two, they have to be orthogonal, right? And they should be orthogonal eigenvectors of this guy. So for this to be satisfied, P has to be an orthogonal eigenvector of Cx according to the linear algebra. Like P has to be a matrix of eigenvectors of Cx, and it has to be orthogonal. That's that. What else again? So, like, I wanted to talk about eigenvectors. So, like, so let's say you have a matrix A and you have B. This will be called AB. So this is a matrix, this is a vector, this is a scalar, and this is a vector. So if this relation, like if it holds, then V is an eigenvector of this matrix. So an eigenvector of a matrix is one that when you apply a transformation on that vector by that matrix, it's going to just give you an effect of scaling that vector. So this is an eigenvector, and the scale is going to be the eigenvalue of that eigenvector.
It's crazy.
I should be. Wow.
Very, very long.
Okay, so an eigenvector of a matrix, like if a vector is an eigenvector of a matrix, it means that when you multiply that matrix and that vector, the effect you get is just that you are scaling that matrix. Like it's just an effect of scaling, which is here. Yeah, it doesn't. Yeah, which is so like if V is an eigenvector of A, then performing a transformation on V, like when I say transformation, I mean multiplying A and B. The effect is going to be like scaling. Like
what is an example?
Yeah, A is this. Yeah. So you have this. You have this. You have this. Before A. So this A, B, B, right?
So what does it mean to transform a matrix? Yeah? So what do you do to, like, once you transform, what happens? Like, if you say you scale a matrix, like, can you give me a practical example? What's a practical example that comes to mind? You take a picture, picture is a matrix, and you perform transformation. What do you think? Like, can you enlarge? Yeah, like you enlarge. What is like? What? Or you share, you shrink it. Yeah, you're transforming. You're practically just multiplying with some angle and some like that means you can change the axis. Do you understand? But this guy there does not, like, it skips the axis first. You can only move it up, down, cannot do anything. So that's like the important aspect.
Okay, so from this notation, I get is correct. A is a scalar value.
Yeah.
A matrix capital A.
Of what?
A matrix of A, that capital A.
No. A is just
A is a value.
A is the value.
A scalar value.
Let's see. Let's not see this. Right, because it's scalar.
Of what exactly?
Okay.
What
So
does the
I want to
scale?
understand the
wait. Okay.
The scale is certain vector V. This V here. So the effect this
Let's say you
is
have
having is the same as that
let's say this is
A multiplied by
1, 2, 3. and you are getting 2, 4, 6. What happened here? Let's say you have 1, 2, 3. So AB equals something. AB equals something.
Like A, B equals B.
So
Like
this
normal
is
popular. Right?
This is B, and this is your. So what do you think happens?
A is something that
A is a matrix. It multiplies B to get this vector. So what happens? What can you say about this and this?
So 2 multiplies the scalar value of 2 minus the vector, then to give one extra.
So what happens? So you have, like, you still have your vector.
Yeah.
You still have your vector. Then you have this scalar here. So meaning that I'm transforming this vector with this matrix, like doing this matrix multiplication, didn't really like the only transformation is it applied to this vector. It just scale it, like it just scales it.
Can I chip in something?
Yeah, chipping.
You know, that it's not the matrix that you are transforming. It's the vector that you are transforming with the matrix. Do you understand? So that can be a little bit confusing. When you say a matrix that is special, you think it's the vector that you are multiplying with the matrix. No, as a matter of fact, it's the matrix, you are multiplying this vector with this matrix.
Okay. So like this is an eigenvector. Like if this happens, then this vector is an eigenvector. And it has an eigenvalue, which is this. So the eigenvalue is that scalar that it is killed by when you perform the transformation on it. So and a matrix can have so many eigenvectors. Yeah. So this cannot be the only eigenvector of this matrix. So you can have more than one eigenvector, and each eigenvector has a corresponding eigenvalue. So let's say you have a matrix of eigenvectors. Not an eigenvector, like a matrix. So let's say this is the matrix of eigenvectors. This is going to give you what? It's going to give you something like this.
No, that's not diagonal matrix.
Yeah. The difference is where so you have something like this now. So you have A multiplying this. This is a matrix of eigenvectors. So this is like Q1, Q2, Q3.
Like you're not dealing with just one anymore now.
Right? So this is an eigenvector, this is an eigenvector, this is an eigenvector. Then it's going to give you just
Eigenvectors. Diagonal is their eigenvalues. Diagonal matrix is their eigenvalues.
I didn't do this well, we get so this is like a diagonal vector. Sorry, the diagonal matrix of
What exactly?
so
So the matrix can be any kind of symmetric, whatever.
yes. Yeah. Okay, so this is the matrix, this is the eigen, so this is the matrix of eigenvectors, and this is the diagonal matrix of eigenvalues. So what you do in singular in eigenvalue decomposition, what you do in eigenvalue decomposition is that you have A. So to decompose A into its eigen vector matrix and eigenvalue diagonal matrix, you are going to get something like this. So you get Q, B, matrix has mean of 0. So x1 will have mean of 0, and the standard deviation is going to be 1. The mean here is 0, STD 1. The same thing for this also. So if I actually calculate the standard deviation, I'm going to get 1 for everything. And the mean also should be 1. Let me try the mean. Sorry, it should be 0. So the aim is to get mean of 0 and standard deviation of 1. That's what you do in feature scaling and normalization. And this is actually 0, right? Or is it minus 5?
Minus 0 or something.
It's 0.000000000.
This is not minus 5.55. This is 0. You can see it.
Yeah, 0.
Like, who can see it? And this is also 0. This is also 0. So like this
Approximately
is like
0.
this is like minus 5 point whatever times 10 power minus 17, which is 0.
Approximately 0.
It's 0. This is 0. To me it is 0.
It's approximately.
So this is 0, this is 0, and this is 0. Okay, then so this is how you find the covariance matrix using that formula I showed you earlier. Yeah, this formula here. So you find the covariance matrix using this formula, and you can only use this formula if your mean is 0, because covariance is that actually your feature minus the mean transpose them. But if the mean is 0, then you can use this.
How many more minutes do you need?
I'm done already. So this is your Cx. So this is the covariance matrix of x. So you calculate it using this formula, you get Cx as this. And as you can see, you have 1 here, 1 here, 1 here. So meaning that the first feature is highly correlated with itself, which is normal. Like x1 should be dependent on x1. It's the same thing. The covariance should be very high. If it is 0, then something is wrong.
Okay, you said we should have something close to 0. Okay, but that was fine.
Yeah.
How come?
Yeah.
Why do you have
Below which one? This one?
Yeah,
This one here?
that's one.
Yeah, I'll get it. So this is 1, this is 1, this is 1, right? And the covariance here is 0.56 something. So remember earlier I said that this is a very funny feature matrix, in that this is x1, this is x2, this is x3, and x3 is just a multiple of x2. So meaning that x2 and x3 will be highly correlated, like highly correlated. So when you come here, this is x2 and this is x3. So the correlation between x2 and x3 is also like it's the same thing. And this is also the correlation between x2 and x3. Because they are the same thing. You can see this x2, this x3. The same thing.
Yeah, it's
Like,
one is scaling the other. You
so
can.
it's like the same thing. There's no difference between x1 and x3. The same thing. This is actually okay. So for you to now do the PCA, right? So the first thing you get is the matrix of eigenvectors for the covariance matrix. So when you do eigen decomposition on this covariance matrix, you get the eigenvalues and you also get the eigenvectors. So this P is a matrix of eigenvectors. But in this case, P is something like this. So the first row is an eigenvector. The second row is an eigenvector. Like the eigenvectors are in the rows. So this is B. This is B here. So this is like it has 3 eigenvectors. So this is the first eigenvector. And you can see that this is 0. Right? The third eigenvector is 0. Meaning that for this feature matrix, we shouldn't even have a third dimension at all. That's why you are having 0 as your third eigenvector. Because in the first place, you just have just 2 features. Like there's no third feature. So, and this is the matrix of eigenvectors, P. So each row is an eigenvector. And you can see something. The second and the third eigenvector are the same thing because of the data we are using. Like we should just have 2 features. So that's why we are having same thing here. You just have to take note of shapes. Like that's why you are seeing dot T, so you can see I did T. I did this too.
Then you
And
transfer.
I did this.
Yeah.
So I did that and I got this. So this x1, this x2, and this x3, and x3 is 0.
Yeah.
This is the 0, like they are all the zeros. 0, 0, 0, 0. Because we shouldn't have the third dimension. We should just have 1, 2.
Okay.
Wait, okay, sorry. Yeah, use it here. So this is 0, right? So using scikit-learn, you don't need to know anything about the covariance matrix, you don't need to know anything about eigenvectors, you don't need to know anything about linear algebra at all. So all you need to know is from sklearn import decomposition. So you want to do decomposition anyway. So you don't want to do PCA. So from the decomposition module, there's a class called PCA. So you instantiate a PCA object using this. I can see here I put my number of components to 3 because I want 3 components. So I have 3 features, so I can actually set this to 2 or 1, but I can't make it 4.
It means you want to decrease.
Yeah. But I just made it 3. Then you just call PCA.fit transform, then you pass in your feature matrix. And what this line does this. So remember, you've not calculated. The matrix of eigenvectors. You don't know what the eigenvalues are. Like you have no knowledge about all these things that are happening behind the big
But
thing.
you know how to
Like
use
you just call this fit transform and you pass in this, and it will return this to you. And that's all. So let's assume, okay, that's all. So this x1, this x2, and you can see that x3 is also 0 also. So you can compare that with this one here. So it's almost the same thing, right? The same thing. So let's assume I use 2. You just take me 2.
it just takes out the extra.
Yeah. Take that one out. And the way it does this is that, like, it will look at the eigen values, right? And will take the highest eigenvalue as the first one. So meaning that the eigenvalue for this is very high, and the eigenvalue for this is also high. Why the last one is low? So for example now, like when I go to my own implementation, so this is my my vectors of eigenvalues, and as you can see, for the first feature I have this for the second feature, and I have same thing over there. So if I'm to set my number of components to be 2, right? So scikit-learn will just calculate the eigenvectors, and then since I'm taking just 2 components, so it will come here and pick these 2 and knock out this guy. So if I select just 1, it will pick this.
The highest.
Yeah, it will pick the highest. So that was what it does, and I think that was all. So for reference, there's a guy called Sebastian Gascar. Sorry, that's not the spelling of his name. I've forgotten. So Sebastian Gascar. So he has a post on implementing PCA. Let me see. Sorry. Yeah. So this is his post on PCA. So he did a lot. He used sklearn, he used, like, he found covariance matrix, eigenvectors. Like, his own was more, practical. Like, he wrote code for it. But this other guy, Vicky Sharp Tuma, like, he also has a post on understanding PCA. And yeah, so this is his post. So his post is more about this. So this guy did more of this, of the maths and understanding covariance matrix, variance, and eigenvalues and all that. So you can check them out.
Any questions, guys? Any questions? So actually, today is the last class for this cohort, and that's amazing. 15 weeks, I mean, like, this is 15 weeks. Like, I really want I know this is not for Lawrence. We need to do it properly. Like, we need to appreciate him properly for taking time and the patience to go through this curriculum. It's not easy, so please do give him a round of applause. Thank you so much, Larry. Thank you so much. To be honest, it's not like it's being paid or anything. I remember specifically that we wanted to start this course, and I was like, who has done introduction to machine learning by Andrew before? I just messaged George, and I messaged her and said, Alpha guy, will you be able to take this class for the next 16 weeks? He didn't think about it. You know, when it's a thing when someone say you did something for someone, you're like, let me think about it more. It was just like, yeah, no problem. So, and he's here, and I know it's not like been easy. He has to go to work, he has to prepare for class, and both of them, and complete, yeah, and be a badass at his work. It's really, really not easy. So I'm really, really grateful that he accepted to do this, and I look forward to him accepting much more in the future. So thank you, Laura. Thank you so much. Yeah.
Thank you, everyone.
Okay, so we are like 25 minutes behind. We're supposed to start the next class by 12:30. Like, I deliberately timed to this class because we have a lot to jump up. 12:35, but now we're like I think 19 minutes behind or something. But anyways, I hope John was not like, I'm really sorry. I planned to be on time, but to participate in this, it's a deep learning hackathon. It means that what the problem we're trying to solve is on image recognition. So there's even a bunch of tutorials to help you go through it. And I think I would expect almost everyone to have submitted because it was one of the projects that we did here, fashion area. So I'm surprised that there's just like resubmission. I don't understand, guys. Just stop your. Is it you don't understand how to submit on Kaggle or something? Like, if you have a problem submitting, that's why we have Lawrence on the group. You know, I know, right? I'm sorry, Lawrence. It's just I exploit you. I'm doing reinforcement and exploitation. So I'm really sorry. So if you have problems, legit problems, don't waste all our time, you understand? But legit problems that you can bring forward, just message him or message me, and I will help you message him if I don't understand how to use it. Or I will direct you to where you find the resources, how to solve your problem. But all I'm saying is that try to get your submission on Kaggle. Like this week, like tomorrow, they're home, they're trying to start. Just dub your own project or go and borrow your friend's project and learn how they did it. If you did it on MNIST, but it's allowed. If you did it on MNIST and your friend did fashion MNIST and you feel like it's completely different, no problem. Then I have fun now with this fashion MNIST. I need to do this hackathon too. Like, let me see your notebook. It's allowed. At the long run, while you are checking the notebook and trying to submit, you would have gotten one or two things. But you know, eventually, if you don't look at it very well, on the day of the hackathon, it might not come first. You understand? And it's first that will collect prize. You get what I mean? And the price is actually quite interesting, though, because Intel sets in their devices. I requested for device, so that like it's kind of like interesting. I don't know. I'm saying this so that you can. You understand? So please guys, I want us to do this for us. Just put your submission there. You can do it because it's your problem. Please do it for help us become greater now. So yeah, with all that being said, you should totally pay attention to this. Some of us had questions on CNN, you didn't understand. You just saw one book like that, Dog, and it's fine. Dubbing is fine for starters. But now it's here to explain how it works. Do you understand? So please do pay attention to our own advantage. So advantages can help you while you're trying to solve your problem next week. Not sit with your teammates. Do you understand? Thank you so much. So yeah, John is scheduled from 1 to 2 p.m. actually, so it's an hour class.
Okay.
Is that you?
30%.
Is what?
13% is going to go up.
Yeah, we need to then can we borrow? No, George.
Stanley is around. Well,
You want to change phone? Is that what it is?
yeah, let's use Stanley's phone. Because my phone will die and it won't come on.
How do I get straight together?
I don't know.